गुड मॉर्निंग स्टूडेंट्स। एमएससी फाइनल के पेपर 5 ऑर्गेनिक सिंथेसिस में आज हम रिडक्शन का चैप्टर स्टार्ट कर रहे हैं। वी स्टार्ट विथ व्हाट एग्जैक्टली रिडक्शन इज। सी, वी कैन डिफाइन रिडक्शन इन 3 ways. It is either the removal of oxygen or the addition of hydrogen or the addition of electrons to an organic substance. So we can say that the reductive process can be put into 3 categories. If in a reaction the removal of oxygen is occurring, or the addition of hydrogen is occurring, or the gain of electrons is taking place, then we say that reduction is taking place in this reaction. Again, the addition of hydrogen can be subdivided into 2 processes. The one is hydrogenation. Hydrogenation is the addition of hydrogen to an unsaturated system. You can see the example here. यहाँ पे एक एल्कीन है. इस एल्कीन में हम हाइड्रोजन का एडिशन कर रहे हैं in presence of a catalyst and we are getting a saturated product. The second one is hydrogenolysis. Hydrogenolysis is addition of hydrogen. It takes place when we take a substrate which is saturated. In a saturated substrate reactant, addition of hydrogen occurs with a concomitant bond rupture. A bond is ruptured and hydrogen is attached. Here is the example. This is ether. The substrate is ether. This is a saturated solution, saturated compound. We are adding hydrogen in presence of a catalyst. The bond breaks between C and O and we get two products. This is toluene and this is alcohol. तो जब सैचुरेटेड कंपाउंड में हम हाइड्रोजन का एडिशन करते हैं इन प्रेजेंस ऑफ कैटलिस्ट, तो बॉन्ड ब्रेक होता है और हाइड्रोजन अटैच्ड होती है, हमको प्रोडक्ट्स मिलते हैं, वो भी सैचुरेटेड होते हैं. दिस इज सेकेंड एग्जाम्पल ऑफ हाइड्रोजनोलिसिस. Here the bond between C and N is being broken and we are getting these products. अब mechanistically हम बात करें तो there are 3 pathways for reduction to take place. The number 1 is addition of electrons. This addition of electron is followed either by uptake of proton or by coupling of free radical. The first example is here. This is scheme 1. यहाँ हम इलेक्ट्रॉन्स का एडिशन कर रहे हैं. देखिए, एक इलेक्ट्रॉन का एडिशन हो रहा है, इसलिए होमोलिसिस अकर्स. इन द फर्स्ट स्टेप होमोलिसिस अकर. दिस डबल बॉन्ड इज broken. One electron goes to this carbon and other electron to this carbon. Again, this double bond is also broken. One electron goes to this carbon and other one to दिस कार्बन. अब इस कार्बन का एक इलेक्ट्रॉन और इस कार्बन का एक इलेक्ट्रॉन मिलके एक बॉन्ड बना देता है. यहाँ देखिए, ये जो इलेक्ट्रॉन ऐड हुआ था वो इलेक्ट्रॉन यहाँ ऐड होता है, नेगेटिव चार्ज आ जाता है और यहाँ एक इलेक्ट्रॉन रहता है तो फ्री रेडिकल बन जाता है. इन द नेक्स्ट स्टेप अ प्रोटॉन इज एब्स्ट्रैक्टेड फ्रॉम अ कंपाउंड. हेयर ROH, a proton is abstracted from alcohol. This proton get attached to this carbon because here negative charge is present on this carbon. So this proton get attached to this carbon. In next step, one more electron is added here and negative charge, a full negative charge is formed. Again a proton is abstracted from ROH and we get this product. Here a molecule of hydrogen is attached to the substrate and this occurs through addition of electron and later the uptake of proton. This is scheme 1 and in scheme 2. This is scheme 2. Here again addition of electron occurs. Homolytic fission of CO bond takes place. One electron goes to carbon, one goes to oxygen. The electron which is being attached goes to oxygen. We get this intermediate. This is a free radical and this is free radical anion. The coupling occurs through this free radical carbon. This is the intermediate that we get. Two protons get attached to these anions, oxygen minus, and we get a product, diol. This is scheme 2 and it takes place through addition of electron followed by coupling of free radicals. The second way by which reduction can occur is the transfer of hydride ion. हाइड्राइड आयन कहाँ से ट्रांसफ़र होंगे? जब हम रिडक्शन कराते हैं कुछ ऐसे कॉम्प्लेक्स मेटल हाइड्राइड्स के साथ विच आर रिच इन हाइड्राइड्स सच एज मेटल हाइड्राइड्स ऑफ बोरॉन इन एल्यूमिनियम एंड एल्कोक्साइड्स ऑफ एल्यूमिनियम, जब इनकी प्रेजेंस में रिडक्शन कराया जाता है तो हाइड्राइड का ट्रांसफ़र होता है. यहाँ ये एग्जाम्पल है लिथियम एल्यूमिनियम हाइड्राइड के साथ हम कीटोन का रिडक्शन करा रहे हैं. फर्स्ट स्टेप में देखिए लिथियम प्लस ये ऑक्सीजन के पास आ जाता है बिकॉज ऑक्सीजन हैज़ लोन पेयर ऑफ इलेक्ट्रॉन्स. इन द सेकेंड स्टेप कंप्लीट ट्रांसफ़र ऑफ CO pi electrons takes place. Oxygen gets minus charge, carbon gets plus charge. A hydride from this AlH4 minus get attached to this carbon positive and we get this intermediate. In the next step hydrolysis occurs and H plus from water get attached to O minus and we get a secondary alcohol. This is reduction of ketone through lithium aluminum hydride and product is a secondary alcohol. This is reduction by transfer of hydride ion. The third one is addition of molecular hydrogen in presence of some appropriate catalyst. This is called catalytic reduction and this reduction is carried out in presence of molecular hydrogen and some catalyst. The catalyst which are used usually are palladium, Raney-Nickell, Adams catalyst and many others. These are the examples. This is the substrate which has two unsaturated sites. This is CO and this is alkene. This catalytic hydrogenation reduces specifically the C double bond and we get this product where this CO double bond is left untouched. Second is a simple catalytic reduction of an alkene and we get the saturated product. Now we have seen three methods, three ways to carry out reduction. Each method has its own advantage. In many reductions, we can use either of the method, but complete reduction of unsaturated compound can be achieved without any difficulty. Our aim is to selectively reduce one group in a molecule which has more than one unsaturated sites. Both catalytic and chemical methods of reduction offer considerable scope in this direction and we choose the method keeping in mind the stereochemistry of the desired product. Some of the examples of specific reduction is, यहाँ देखिए जब हम ये वाला reducing agent यूज़ करते हैं, this is tertiary tributyl stannous hydride. जब हम इसे यूज़ करते हैं तो hydrogenation can occur at two sites. This is an alkene and this is a carbon which is attached to bromine and chlorine, bromide and chloride. What happens is the reduction can occur at both places. Here hydrogenolysis can occur and here hydrogenation can occur. But when we use this specific reducing agent, then hydrogenolysis occurs and both chloride and bromide are removed and we get this side where hydrogen is a molecule of hydrogen is get attached to this carbon, and this CC double bond is left untouched. In the second example, Lindlar's catalyst is used, and this C triple bond C is reduced to get an alkene. In the third example, sodium borohydride is used as catalyst, reducing agent, and we get a product where only CO bond is reduced and this COO bond is left untouched. तो जब हमें प्रोडक्ट पता हो, when we know what product we want to get in a reaction, then we use a specific catalyst, specific conditions where we get only the desired product as the end product. Next हम पढ़ने जा रहे हैं कुछ compounds का reduction. सबसे पहले हम पढ़ेंगे reduction of hydrocarbons. Reduction of hydrocarbons में जो सबसे पहले हम ले रहे हैं वो है alkenes का reduction. Reduction of alkenes. The first method by which reduction of alkene can occur is catalytic hydrogenation. Catalytic hydrogenation is one of the most convenient method for the reduction of alkenes. The method consists in we stir the product with the we stir the substrate. We take a substrate, a reactant, and we stir it with the catalyst in a suitable solvent, and then we pass hydrogen gas through this solution. Catalytic hydrogenation can be classified into two categories. This classification is based on the homogeneity of the reaction. The first is heterogeneous hydrogenation. A number of hydrogenation catalyst is used for catalytic hydrogenation. Nowadays, we use a transition metal catalyst such as rhodium, platinum, palladium, etc. These catalysts are adsorbed on a solid support such as carbon or alumina. The catalytic reduction takes place between gaseous hydrogen and an organic compound. See what happens is, this is the example. This is the surface, this is a solid support surface such as carbon. The catalyst is present on surface of this carbon. In the first step, hydrogen gas is passed through this solid support which has catalyst on its surface. The hydrogen gas is adsorbed to this catalyst. We can see this is the hydrogen gas and this is adsorbed on the catalyst surface. Then we pass the alkene. Then we pass alkene, the organic compound, through this catalyst. Here again the organic substrate, it also get attached to the catalyst. This is the catalyst surface. Hydrogen is already attached here, and here the organic substrate also get attached. So this catalyst surface provides a place where this organic substrate and hydrogen can come in contact. So reduction takes place at the surface of the catalyst, which adsorbs both hydrogen and the organic compound, and this surface facilitates their contact. Transfer of hydrogen takes place from the catalyst to the molecule. C. One hydrogen get attached to this organic substrate. Here it is alkene. This is half hydrogenation. In the next step, one more hydrogen get attached to this carbon and we get the product. Transfer of hydrogen takes place from the catalyst to the molecule, and this results in reduction and we get a saturated product. Although elevated temperature and pressure invariably increases the rate of hydrogenation, but this reaction can take place in a satisfactory manner at room temperature also. Experimentally, it has been found that addition is not a complete syn addition. You can see here, this addition is a syn addition because हाइड्रोजन, यहाँ देखिए हाइड्रोजन का मॉलिक्यूल और जो एल्कीन है वो इस तरह से एक दूसरे के कांटेक्ट में आते हैं that only syn addition can take place here. But experimentally it has been found that this addition is not 100% syn addition. We get both the products. Although the syn product is the major product, but we get anti-product also. This is an example for that. Here 82% of syn product is found and 18% of anti-product is formed. Lack of complete syn addition may be explained if we suppose that all steps except the last one are reversible in this scheme 5. Except from this last step, all other steps are reversible. Next, the ease of reduction of an alkene decreases with the degree of substitution of the double bond. More the substitution, less is the ease of reduction of a double bond. The example is, see, here two types of double bonds are present. One is this one and the other is this one. This double bond has 3 substitutions, 1, 2, 3, and this double bond has 2 substitutions, 1 and 2. Less the degree of substitution, more is the degree of reduction. So this double bond get reduced and this double bond is left untouched. So ease of reduction of an alkene decreases with the degree of substitution of the double bond. This is an example of this fact. In contrast, the isomeric compound of 1. See, if this is the substrate, in this substrate, both the double bonds have same degree of substitution. This double bond has 2 substituents and this double bond also has 2 substituents. So this molecule get reduced completely and we get this product where both the double bonds are completely reduced. Now we will see some examples of selective reduction. These are some of the examples of selective reduction. Selective reduction of carbon-carbon double bonds in compounds containing other unsaturated groups can usually be accomplished. The best catalyst for catalytic reduction is palladium. If the reduction occurs in presence of palladium, then selective reduction of double bond, CC double bond, can take place. These are some of the examples for this. Here, reduction can take place at cyanide and CC double bond. Reduction of cyanide can take place and CC double bond alkene can take place. But when we use palladium as catalyst, then selective reduction of carbon-carbon double bond occurs. Here also we have 2 groups. In the second example we have 2 groups, nitro and alkene. If we use palladium, then this nitro is untouched and reduction of CC double bond occurs. In the third example, reduction of CC double bond occur and COO group is left untouched. The second is homogeneous hydrogenation. For homogeneous hydrogenation, Wilkinson's catalyst. This is triphenyl phosphorus rhodium chloride It is the most useful homogeneous catalyst for alkenes. This catalyst is soluble in solvents such as methyl alcohol and ethyl alcohol. First, we dissolve this catalyst in either of the solvent, methyl alcohol or ethyl alcohol. This solution is red in color. Addition of hydrogen to this solution of catalyst promotes the formation of a complex. The formation of complex takes place by oxidative addition of hydrogen and dissociation of bulky phosphine ligand from the metal. Dissociation of a phosphine ligand opens up a coordination site for the alkene to attach itself to the metal. The next step in the mechanism is the concerted addition of a metal hydrogen bond across the coordinated alkene to form complex B. Both atoms, hydrogen and rhodium, are added syn fashion to the alkene. Finally, reductive elimination leads to the formation of the product. C. The mechanism of this reduction involves, in the first step, addition of hydrogen. Addition of hydrogen to the solution of Wilkinson's catalyst occurs in the first step. यहाँ देखिए रोडियम के साथ ये दोनों हाइड्रोजन के एटम्स अटैच हो गए. In the next step, a bulky phosphine ligand leaves this intermediate. यहाँ से एक phosphine ligand बाहर निकल जाता है and we get a complex. This is complex A. In the next step, addition of alkene occurs to this complex A. When this bulky phosphine group leaves the intermediate, leaves the compound, a coordination site opens up for the addition of this alkene. एक रोडियम की साइड जहाँ से ये फॉस्फीन बाहर निकल गया था, वो वाली साइड हमारे पास अवेलेबल है जिसके थ्रू ये एल्कीन इस रोडियम के साथ अटैच हो सकता है. ये देखिए, ये रोडियम के साथ एल्कीन अटैच हो गया. नाउ this hydrogen from rhodium get attached to one of the carbon of alkene, and this rhodium attached to other carbon of the alkene. This is a concerted reaction, concerted addition, where both hydrogen from the complex and rhodium from the complex get attached to alkene substrate, organic substrate. So this is a syn addition. This bond between hydrogen and rhodium breaks and this hydrogen get attached to this carbon completely. In the second step, the other hydrogen from the rhodium complex get attached to other carbon, and this bond between carbon and rhodium dissociates and we get the product, the saturated product. This is the reduction which takes place when we use Wilkinson's catalyst as the reducing agent. This is another example of Wilkinson's catalyst. Syn addition is shown by catalyst reduction of malic acid. This is malic acid and we are adding deuterium to malic acid in presence of Wilkinson's catalyst. This gives mesodideutyrated succinic acid. If we use fumaric acid, this is fumaric acid. If we use fumaric acid, then we get racemic mixture of fumaric acid. And if we use malic acid, then we get mesodideutyrated succinic acid. This catalyst is used for the hydrogenation of non-conjugated alkenes. Wilkinson's catalyst is best used for the hydrogenation of non-conjugated alkenes. Functional groups such as oxo, nitro, cyano, halo are not reduced under the reaction conditions in the presence of triphenylphosphine rhodium chloride, that is Wilkinson's catalyst. There are some of the examples for this. If we use Wilkinson's catalyst in compounds which has double bond along with some other groups which can also be reduced, then reduction takes place at only the double bond and other groups are left unreduced, untouched. These are some of the examples for this. This is the first example where nitro group is not touched and reduction occurs only at carbon-carbon double bond. In the second example, cyanide group is not touched and reduction occurs at this side. And in the next example, third example, reduction occurs at this side only, because although this compound has two alkenes, two alkenic group and one CO group, but only this alkene, this CC double bond is reduced because it is least substituted and the other one is left untouched. Mono and di substituted double bonds are reduced much more rapidly than tri and tetra substituted double bonds, permitting the partial hydrogenation of compounds containing different types of double bonds. This is example for this. Here also only this group is left untouched and this CC bond is reduced because it is mono substituted, whereas this is tri substituted double bond. This double bond is CC bond is tri substituted 1, 2 and 3. So this is left untouched and only this CC double bond is reduced using Wilkinson's catalyst. The next one we are taking up is reduction with 1A metal and in liquid ammonia. Alkenes that are substituted with an electron withdrawing groups. यहाँ ध्यान दीजिए, we are talking about alkenes which are substituted, which are attached with an electron withdrawing group on olefinic carbon that can be reduced with lithium, sodium or potassium, which are group 1A metals, in liquid ammonia at low temperature. The reduction is generally carried out in presence of a proton donor, that is ethyl alcohol or tertiary butyl alcohol. Alkenes having no electron withdrawing groups are unreactive for this reagent. So this is a very specific reagent which reduces only the double bond, only the olefinic carbon which is attached to an electron withdrawing group, and other olefinic groups are left untouched in this reaction. See the examples. These are the examples. In the first example, this is the olefinic double bond and we have this CO bond. This is attached to the carbon, olefinic carbon. This CO group is electron withdrawing group. So if we use sodium or 1A group metals in liquid ammonia, then this olefinic carbon get reduced. This is another example for this. Here again CO group is attached to carbon which has olefinic double bond, and we carry out reduction using sodium dissolved in ethanol in presence of liquid ammonia. This is another example for this. Next we will talk about the mechanism of this reaction. In these cases, reduction of double bond takes place via formation of radical anion. Here the transfer of electrons occur. We have talked about this when we started the chapter. Here the reduction occurs through transfer of electrons. Homolytic fission takes place. Whenever transfer of electrons is taking place, homolytic fission is the first step. Homolytic fission of carbon oxygen double bond occurs here, and we get this intermediate which has a free radical at this carbon and anion on this oxygen. These two are the resonating structures of this radical anion. In the next step, abstraction of proton occurs and we get this free radical. Again, one electron from sodium, transfer of one electron from sodium takes place and we get an anion at this site. The H plus from this oxygen get transferred to anion at this site. So this hydrogen from oxygen get attached to this carbon here. In the next step, these pi bond electrons transferred to this carbon and this bond between O and H ruptured and electrons transferred between oxygen and carbon. H plus from here get attached to minus charge at this site and we get the product where reduction of double bond has taken place and we get this product. This was the reactant which has this C double bond O bond group and a double bond CC olefinic bond here. This CC olefinic bond is attached to electron withdrawing CO group and reduction of this CC olefinic bond has taken place and this is the product. Next we are taking reduction with diimide. Diimide is an unstable compound and it is prepared in situ, usually by the oxidation of hydrogen. This is oxidation of hydrogen or by thermal decomposition of para-toluene sulfonyl hydrogen. This is para-toluene sulfonyl hydrogen. If it is decomposed, when it is decomposed, we get diimide as product. And the third way is by azo-dicarboxylic acid. This is azo-dicarboxylic acid and it is decomposed to get diimide. Diimide is a very selective reagent for the reduction of carbon-carbon double bond. The reaction of diimide with alkene is a concerted group transfer reaction proceeding through a 6-membered cyclic transition state. This is the 6-membered cyclic transition state and this is a result of a concerted reaction in which reaction takes place between diimide and alkene and we get this cyclic transition 6-membered transition state. It results in predominant syn, that is cis addition of hydrogen onto a double bond. The mechanism explains the high stereospecificity of reaction. See, we get a cyclic transition state. This cyclic transition state explains the stereospecificity, the syn stereospecificity of this reaction. The formation of nitrogen is a driving force for this addition reaction. A molecule of nitrogen is formed and this is the driving force for this reaction to take place. Some of the examples of reduction using diimide are given below. When diimide is used to reduce malic acid, we get mesoform. If we use this acid, fumaric acid, we get a racemic mixture of succinic acid. In this reaction, this CC olefinic bond get reduced and we get a syn product, and the next reaction also this double bond is reduced and this NO2 group is left untouched and we get this product. These are some of the examples of reduction through diimide, and this diimide is a very important reducing agent टू रिड्यूस कार्बन कार्बन डबल बॉन्ड। तो आज हमने रिडक्शन पढ़ा हाइड्रोकार्बन्स का और हाइड्रोकार्बन्स में भी एल्कीन का। नेक्स्ट लेक्चर में हम एल्काइंस के रिडक्शन के बारे में बात करेंगे। थैंक यू।